Hello and welcome to The Effect. This is the last video for the partial identification chapter, which means it's also the last video that I plan to make on this series for a while, although who knows, we'll see what happens. This video is about the topic of applying partial identification in the context of matching. So this is actually a strange one. So remember, partial identification, right? We're dealing with the case where we don't want to make strong assumptions, right? If we want to usually do matching, what we do is we pick a set of matching variables. We take our treated and our control groups. We find a set of matching weights, or we pick matched pairs. And the assumption that we then have to make is that we have closed all the back doors, right? I've matched on the full set of variables that allows me to close every back door that I need, such that that matched pair that I have, they are perfectly matched. If you wanted me to guess which one of these two was the treated one, I wouldn't be able to tell. In a propensity score setting, for example, let's say that I've got a treated value that is a propensity score of 0.25, right? 25% chance that they were treated. They did happen to get treated. There was only a 25% chance that they did. I would match them maybe to somebody with another 0.25 propensity score. They each had a 25% chance of being treated, which means that if I just look at them and I don't know which one's treated, I can't actually tell which it is. And that's what we want, right? We want it to basically be random which of these two happens to be treated and which isn't, and they're basically comparable otherwise. Now, that's a strong assumption. We are assuming that we have matched on the full set of variables that we need to close all the back doors. Probably there's going to be something that we have left out. But we also don't want to just say, well, there's some bias left. I haven't matched on everything. I'm going to go home. I give up. Right? We want to go somewhere in the middle. We're going to say, okay, I know that we have not perfectly gotten rid of all the back doors, but let's see a reasonable range of assumptions we might be able to make about how much bias we've gotten rid of and how much bias might be left, and see what we can say anyway. Maybe we can get a range of estimates instead of a point estimate. We can still say something. So how can we do this in the context of matching? Now, this actually gets a bit tricky because the most common by far way of doing partial identification in matching is something called Rosenbaum bounds. There's a problem with Rosenbaum bounds, which is that they're very much designed to work in one specific context, which is this. You are doing propensity score matching, and you are picking sets of matches rather than doing inverse probability weighting. If you remember back to the matching chapter, I basically said, don't do that. I said, if you're going to use propensity scores, then use inverse probability weighting. And if you're going to use picking matched pairs, then don't use propensity scores to do that. But the problem is that Rosenbaum bounds are definitely the most common way to do this. And also, they're really intuitively good for getting across the idea of how this works. And a lot of these concepts carry through to other approaches to doing matching. So I'd recommend watching this video for the intuition on how partial identification works with matching. But then if you're going to actually do it, maybe go to the chapter, check out some of the other sources for other ways to do this that don't rely on picking sets of matches with propensity scores. So with that said, how do Rosenbaum bounds work? Well, Rosenbaum bounds, again, we're working with matched pairs. We're picking matched pairs. And when we pick a matched pair, the idea is that they are perfectly matched, right? That, there's no other relevant information that would tell me which of these two groups or which of these two individuals is treated and which one is not treated, right? I simply can't tell. You could tell me all the other information about these two and it would not give me any clue. Or really, maybe I do get some sort of clue, right? I've matched on a bunch of stuff, but if you told me one new thing about them, maybe that would tell me which one of these two is treated, right? I might be able to guess more than half the time. It's not a coin flip anymore, right? If I have two people who are truly the same propensity, 25% chance each to get treated, I shouldn't be able to tell. It would be a complete coin flip and guess to see which one of these two is the treated one. But if I can tell, suddenly I have a little bit of bias, right? Because if I can tell that this one's more likely to be treated than the other in reality, then I haven't actually matched very well on my propensity score, right? There's some bias left in there, especially if the thing that's omitted is also related to the outcome variable. In other words, it's on a back door. So Rosenbaum bound says this. Okay, so I know that maybe it's not exactly 50-50, right? But I'm gonna put a bound on how bad I think the mismatch might get. That's what I'm going to be willing to do. So unlike in typical matching where you're assuming there's no bias left, you assume that there's zero deviation in the true propensity score between these two, I might say, I don't think it's exactly 50-50, but I'm going to say it's no worse than 60-40, right? Or no worse than 55-45, or no worse than 70-30, whatever it is, whatever the bound is that I think is reasonable, I can impose that bound and say, well, if it's no worse than this, then that gives me a range of estimates. I can still narrow down the estimate of my treatment effect. It's not a single number, but it's going to be a range of reasonable values based on the range of potential amounts of bias between 0 and the maximum amount I'm willing to consider. And we're making that assumption for every single pair in our data, right? So if I'm going to say something like, I think that the deviation, it's not 50-50 exactly, but it's no worse than 60-40, then I'm assuming it's no worse than 60-40 for literally every matched pair in my sample. There is no matched pair in my sample where if you told me more information about them, I would be able to do better than 60-40 at telling you which one's a treated one. Now that range of estimates, we're going to be basically bounding with something called the gamma parameter. Gamma tells us the worst level of mismatch that we are going to allow among any set of pairs in our data. And when you set it up, you get a bound like this. Now that term in the middle, that pi is the probability of treatment, and pi t is the probability of treatment among one of those matched pairs that actually is treated. The pi u is the probability of treatment for the observation that is actually untreated. Now, if those two probabilities are exactly the same, that middle term works out to exactly 50%. But if there's a bit of deviation, if maybe the treated one was actually a bit more likely to get treated, it's not going to be 50%. Or maybe if the treated one is less likely to be treated, it might be less than 50%. But we're going to bound it between these two values. We're going to bound it between gamma over 1 plus gamma on the high end and 1 over 1 plus gamma on the low end. If we assume that there's no mismatch worse than that, then I can also bound my estimate. I can basically say, hey, there's this amount of bias in there. I don't know exactly which direction the bias goes, but it's in there. It's no worse than this. That tells me that my estimate has to be in this reasonable range. And typically the way that you actually do this is you try a number of different gamma values and you see at what level does the mismatch get so bad that I can no longer reject 0 from my treatment effect estimate. I've estimated some effect. I want to know how bad would the mismatch have to be to get rid of my effect. And then I can ask myself, am I willing to believe that the mismatch is no worse than that? Let's use the same example from the last video. So we're looking at a case where we have a bunch of data on people who have been accused of crimes, specifically drug crimes, in the United Kingdom. And the question is there a gender bias in the rate at which these people who are accused of crimes will actually go to prison? And we have a bunch of control variables or matching variables here, things like socioeconomic status, things like the kind of drug that you're being accused of working with, things like do you have kids at home that you need to take care of? Now, some of these things might be related to gender. So, for example, of a matched pair, it might tell me which one's the man and which one's the woman, right? In which case, that would be mismatched because I'm trying to match men to similar women. And it also might be related to whether you actually go to prison or not, and therefore we get a biased result. Now, in this analysis, you do find a gender bias. Men are more likely to go to prison for the same crime than a similar woman who has similar levels of all those matching variables that I mentioned. But of course, there might be something that we are leaving out, and maybe all that effect that we see is just bias. So how much bias would there need to be for this to all go away? Well, when you recalculate it, the effect goes away at a roughly 1.5 gamma, a gamma value of 1.5. Now, the exact value that you get depends on exactly the matching procedure that you use, but in the defaults that I've set here, the effect goes away if gamma is 1.5. So what does that actually mean? Well, if you use that equation from earlier, this works out to not being able to tell them apart more than 60% of the time. So you take a man with a matched woman who is similar on all the characteristics we do see, and then magically, I learn about all the stuff that I didn't see. If all that new stuff allows me to distinguish these two such that I can tell which one's the man and which one's the woman more than 60% of the time, that is enough bias to explain all of my effect. If I can't do it that much, if learning about everything else about these two people only gave me a 55% chance of being able to tell which one's the man and which one's the woman, well, that might reduce the amount of bias that I estimate, but it wouldn't take it all the way to 0, right? That's the question I'm trying to answer here. At what point does my effect go away? How robust is my result? So again, with partial identification, we are asking ourselves, what are the assumptions we actually believe in? I don't have to assume that they are exactly perfectly matched. I also don't have to say, they're not perfectly matched. There's some bias here, so I'm giving up. I'm going home. I can say, how well matched do I think I'm willing to claim that they are? If I think they're well matched enough that I can't tell them apart more than 55% of the time, then I think that the estimate that I had in my original amount is probably good to go. I probably do have some gender bias in this sentencing procedure. If I think that I can tell them apart more often than that, if I happen to learn about all the additional information, well, then I can't prove that there's gender bias. There's simply too much bias in there's too much statistical bias or causal inference bias in my estimate to be able to distinguish that for you. I can't see it. Is that a reasonable assumption? Well, it depends, right? At that point, you still have to argue for whether you think this is a reasonable assumption or not, but you at least know what you're arguing about, right? You no longer have to give up and go home because there's some bias, and you no longer have to make the assumption it's probably not true that you've perfectly matched everybody and there's nothing left. It's just What's the strongest argument that you can make? What's the reasonable claim that you can come to based on the things that you think are actually true about the world? And that is the bonus of partial identification. All right, that is it for these videos on partial identification, the new chapter in the second edition of The Effect. Please do check out the book. I think it's really good. There's not just a new chapter, there's also plenty of new sections in other parts of the book, lots and lots of little tiny updates or big updates throughout. It is worth checking out, and it's free to read anyway, so you might as well go ahead and take a look at theeffectbook.net. Thank you very much.